Okay. So plan for today is this. We'll start talking about deadlock. We'll finish this particular lecture, and then we will spend some time talking about um, essentially the logistics for final exam and the topics for a final exam. And I'll give you a brief idea about the format. So let's start talking about deadlock. So here is a condition, right? Like what is deadlock? Deadlock is system not being able to make progress because there is a contention for the resources. So every process is going to be asking for certain resources, CPU cycles, maybe memory, IO devices, and if other processes are already holding those resources, then you're not going to be able to make progress in your system. So that's that condition, deadlock. So we'll take a look at how we can detect it, how we can prevent it, how do we know whether a deadlock exists in a system or not, and we'll try to learn that using some graphical notations as well, resource allocation graphs or RAGs. Let's take a look at that. So what is it first? Is there a difference between deadlock and live lock? We'll take a look at an example. Then we'll talk about 4 necessary conditions that should hold in order for you to be able to guarantee that there is deadlock. Then we'll, like I said, resource allocation graphs, and then how do we handle deadlocks? How do you handle deadlocks? On your computers, when there is a deadlock, is there a message? There's a deadlock. So how does your laptop handle deadlock? By doing blank. Nothing, right? So they do nothing to handle deadlock. The reason is prevention is worse than the cure. So what is that? No, not prevention. The disease is better than the cure, right? The disease is better than the cure. So the amount of work the operating system has to do in order to make sure that the deadlock doesn't happen is worse for a user experience than just rebooting your system once in a while. So that's what real Windows Unix operating systems do. They don't do anything to prevent deadlock. So why are we studying here? Well, we are going to need to know what causes it so that we can design better computer systems. So even if there is no backup plan, there's no net for us to be able to prevent it from happening or detecting it, maybe we can design our processes, maybe we can allocate resources to processes in a manner that prevents it from happening. So like I said, what is deadlock? It is because of processes competing for resources. So if resources are unavailable, then the process is going to enter a waiting state. And sometimes a waiting state is never able to change state. Why? Because you never get that resource in order to make progress. The requested resource are held by other waiting processes. So everybody is sort of waiting for each other to finish. And that's a deadlock condition where there's no progress. Progress of the system is suspended because of this. Now, progress of the system could also be suspended during a live lock. There is a difference between deadlock and live lock. The difference is in deadlock, processes will go to a waiting state and will not be able to change state. In live lock, processes will be able to go to waiting state and they will be able to change state. But the similarity is both cases, progress is not being made. So they may come back to the ready queue, they may get the processor to work on, but they end up in waiting state again, right? So the progress is being halted, but even though they are able to change state. Next, I think a really good way to explain deadlock is by using this analogy. Now, there's a lot of debate about this. No idea who is true there. This was law passed or just proposed in early 20th century by Kansas legislature. And you can read the law here. That's what it states. When two trains approach each other at a railroad crossing, both shall come to a full stop and neither shall start up again until the other has gone. Great law, right? So there's a lot of debate about this. Like they say this was passed or this was just proposed. So there's no consensus there, but this was something that was real. And you can see that both are going to come there. They're going to make a full stop. No, neither is going to make progress because it's waiting for the other to go through. And this is something very similar to what is happening in deadlock. Every process is waiting for something that is being held by another process. So until you finish, I'll not be able to finish. Because when you finish, you will be releasing those resources, which I can use. But that's not going to happen because you are maybe holding certain resources and waiting for somebody else, right? So that's like a good analogy to a real world example. So we'll start modeling deadlock systems or systems in general, and we'll try to understand whether there's a deadlock existing or not by using some graphs. So a graphical representation of the state of the system in order for you to be able to pick out, oh yeah, there is a deadlock that is possible over here, or there's no deadlock possible there. And for that, we'll use a system model. System consists of resources, CPU cycles, memory, I/O devices, and so on. And resource types could be classified by these: R1, R2, R3, and so on up to Rm. So there are M resource types. CPU cycles, memory space, I/O devices are some that are listed in resource type. Each resource type can have W sub I instances, right? Multiple hard disks, different cycles, so different processors, 2 copies of your I/O devices. So each resource type can have multiple instances. Now, we just have to be careful about 2 different types of resources. They could be shareable, they could be non-shareable. Right? Shareable resources are one resource that could be shared by 2 or more processes. Non-shareable, you're not sharing anything. So like a read-only file. A read-only file is an example of anybody can read it at any time, right? So that's a shareable resource. So resource types, how many resources do we have? R sub I, M resources. And each resource type has W sub I instances, multiple instances of the same resource type. Now, each process is going to do this. It's going to request for an instance of a resource. It is going to use that instance of a resource, and then it's going to release that instance of that resource. Maybe it'll need two instances, maybe it'll need 3 instances, but it'll need some instances of some resource types. Now, in order for us to be able to comment about deadlock, we need 4 of these conditions to be satisfied. If all these 4 conditions are satisfied simultaneously, then you know for sure that there is deadlock that exists in the system, which means that nobody will be able to make progress, nobody will be able to even change state. Now, if only one of them is true, then we can say that the chances of deadlock are there, right? Deadlock may happen, but we cannot say that for sure. The first 3 of these are indirect conditions for commenting about deadlock. The last one is a direct condition. So what makes the last one direct? Well, if you take 4 and if you take just 1, right, 4 with 1 actually guarantees you that you will have a deadlock. So if you have a circular wait going on and you have mutual exclusion, which means that only one resource can be used by any process at any time, then you actually in fact have deadlock. So 4th one is a direct condition. The first 3 are indirect conditions. But all 4, if they are held simultaneously, it guarantees that there is deadlock. So what are they? Let's talk about them. 1, mutual exclusion. What does that mean? Only one process at a time can use a resource. One process, one resource. I'm not going to use the same resource for more than one process, right? So this is non-shareable resources. Next, hold and wait. A process is holding at least one resource and it is waiting for another resource, right? What would be better than that? Well, not better necessarily, but what would be an alternate to that would be, I will not hold and wait. Instead, once I have things available, whatever I need to make progress or to complete, whatever I need, if it is available, then I will take it, complete the process and I will release those resources. But what I'll not do is hold a particular resource, wait for somebody else, and then use that, and then use that, and then use that, and then I'll make progress. So by doing that, I'm essentially going to be waiting for a very, very long time. Maybe, right? Because that resource, that one particular resource, may not be released by one process. So hold and wait increases your chances of deadlock. Next, no preemption. We are not snatching away resources from a process. A resource can be released only voluntarily by a process after that process has completed its task. So what we are not doing is asking a process to release the resources. It can only do that voluntarily. Again, no preemption will increase your chances of deadlock. Last one is circular wait, which is one process waiting for another, waiting for another, waiting for another, waiting for another, waiting for the first one, right? So if everybody is waiting for another one in like a loop, then you are going to have chances of deadlock. And if you can see, if mutual exclusion, if you combine that with mutual exclusion, you can clearly see everybody is waiting for one, there is no shareable resource, you have a deadlock situation that exists there. So let's talk about 4. There exists a set of processes, P0 all the way to Pn. These are all waiting processes, or all these processes are in the waiting queue, such that P0 is waiting for P1, P1 is waiting for P2, Pn minus 1 is waiting for a resource that is held by Pn. And then finally, to complete the loop, Pn is waiting for a resource that is held by P0. So all of them are waiting for each other to complete. It's like that train example. And with only the circular wait, when you graph this, it will appear like a cycle of directed arrows. And if you see the directed arrows, you may think, oh yeah, there is a deadlock that exists over here. But you have to be careful. This is only one condition. It's a direct condition, but it is not guaranteeing you that deadlock exists. It just increases the chances. Questions about these 4 necessary conditions for deadlock? All right, so let's talk about RAGs, resource allocation graphs. How can I represent these allocation or request from a process for a particular resource using a graph? So for this, I will use any graph. What does it have? It has vertices and it has edges, right? So a set of vertices V, set of edges E. Vertices are also called nodes or points in the graph. Edges are also called links, arrows, lines, arcs. Your set of vertices are partitioned into 2 types. You can have a process vertex or you can have a resource vertex. So P, which is set of all your processes, P1 through Pn, this is set consisting of all the processes in the system. Next, resource, R1 through Rm, different number of resources, right? And we're not even talking about number of instances per resource right now. This is R, resources. These are vertices, which represent resource types in the system. A request edge is an arc that is pointing from a process to a resource. So this is process I requesting resource J. And so that's called a request edge. Next, assignment edge. Resource J has been assigned to process I. How are we going to represent these arrows and vertices? Well, for a process, to represent a process, we'll just draw a circle. To represent a resource type with, say, 4 instances, we'll draw a box, and then we'll have 4 more boxes inside that box to represent 4 instances of that particular resource type. Next, request edge and allocation edge. Request edge or allocation edge is also called an assignment edge. P sub I requesting one instance or multiple instances, one instance of Rj. How does that get represented? P sub I requesting a resource of type Rj. Next, how is it holding? P sub I is holding an instance, or that Rj has been assigned. An instance of Rj has been assigned. This particular instance has been assigned to P sub I. So we have got arrows, and then we have got vertices to represent processes and resources, and request edges and assignment edges. This is an example of a resource allocation graph. So essentially, this is a snapshot of the state of the system involving these three processes and these four resource types. Here we have R1 and R3 to have one instance per resource. R2 has two instances per resource, and R4 has three instances per resource, which is not even a part of this problem right now. So let's try to see whether we have a cycle or not. Cycle is one indication of whether a deadlock could happen or not. So if you start at P1, you see, go here, that's it. There's no cycle. Remember, these are directed edges, right? So there's no cycle in the graph. So if you see no cycle in the graph, you right away know that there is no deadlock. You have to remember that these are directed edges. So this is not going to count as a cycle. So how does the system make progress here? Well, P3, if you look at P3, this guy already has what it needs. It doesn't need anything else. P3 will use R3, release it. Once R3 gets released, P2 will use R3. It already had R1 assigned. R2 gets assigned to P2, already is assigned to P2. So P2 gets whatever it needs, and then P2 will be able to finish. After P2 finishes, it will release one resource of type R3, one resource of type R1, one instance of type R2. Once it releases all those resources, P1 can use that. P1 already has that. P1 will be able to finish. You guys see that? Yeah. So no cycle. You don't even have to go further. No cycle, no deadlock. But even if there is cycle, there is a possibility that you may not have deadlock, and we'll show examples of that. Next. Here, let's try to see if we have a deadlock or not. So let's try to see if there is a cycle. P1, cycle. Okay, so there is a cycle, right? So there is a cycle. Let's try to see if actually we will be able to make progress or not. Well, P1 is waiting for R1, one instance of R1 that has already been assigned to P2. P1 has an instance of R2. P2 has an instance of R2, but it is waiting for an instance of R3. That particular instance is waiting for, that particular instance has been assigned to P3. P3 is waiting for one instance of R2. So P1 waits for P2, P2 waits for P3, P3 waits for P1. And all the resources, they already have been assigned or they are being requested. So that's a cycle, even though there is no mutual exclusion here, because here you have sort of two instances per resource type. So mutual exclusion is not being followed here, but this is a circular wait. The fourth condition is being satisfied, and if you can see, the resources are all under contention. We don't. If we had one more resource type of R2, we may have been able to make progress, right? We could have assigned that to P3, and it would be able to finish. So deadlock present with the cycle, but we cannot guarantee it, right? So presence of a cycle may not guarantee deadlock. You have to kind of go in and try to see whether you will have a deadlock or not. Go ahead. Yeah, so cycle doesn't mean deadlock for sure. It increases the chances. Then you start looking at the three other conditions: mutual exclusion, hold and wait, and so on. So over here, because the size of the example was small enough for us to look at all the details and see whether we will be able to make progress or not, we know that there is a deadlock here. But you're absolutely right. A cycle doesn't mean deadlock. Example here. So P1, cycle, 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 right? So there is a cycle there of directed edges. But this doesn't mean that there is deadlock. If you can see here, P2 has been assigned R1, right? So if P2 is assigned R1, it only needs one instance of R1. It will be able to finish. P4 has been assigned one instance of R2. It will be able to finish. Once P2 and P4 finish, what is going to happen? We are going to have two resource types of two instances of R2, two instances of R1. This was already assigned to this guy. This was waiting for one instance type, right? So P4 finishes, one instance frees up, P3 can use that, and P3 can use this. P3 will be able to finish. Once P3 finishes, all the resources are available. P1 can finish. Can you see that? So there is a cycle, but no deadlock here. Questions? No? Straightforward? Okay. So just to summarize what we have learned, no cycles means no deadlock. But if there is a cycle, then there is a deadlock only if there is one instance per resource type. So circular wait along with mutual exclusion will take you to deadlock. However, if there is a cycle and if there are several instances per resource type, then there is a possibility of a deadlock. We would have to go and sort of look at the state of the system in a little bit more detail to figure out whether there is deadlock or not. Next, how do you handle deadlocks? Well, there are lots of schemes. So to ensure that the system will never enter deadlock is one way of doing it. Make sure you never enter into that particular state. So that is deadlock prevention or deadlock avoidance, which is not covered in this particular lecture. So this is, I'm not even going to, so maybe I will choose to starve certain processes. I will never give them what resource that they want. So allocation of resources is being done in such a way that some resources are never getting it, some other processes might be getting the resources, and they may be able to make progress. So if I'm doing that, then I'm preventing deadlock from happening by sacrificing something. What am I sacrificing? I may be sacrificing the fact that I'm starving certain processes. So that's what I meant by the cure is worse here, right? So that is under deadlock prevention or avoidance. The second method, how to handle deadlock, is allow it to enter the deadlock state and then recover from it. Recovery from a deadlock. How would that go? Let's say you get into a deadlock situation. Processes are contending for resources. Nobody is able to make progress. Then what can you do? The operating system can go in, take a look at the state of the system. How does the operating system know whether there is no progress being made or not? Can it do that by monitoring CPU utilization? Yeah, monitor CPU utilization. If CPU utilization is extremely low, even though there are so many process IDs in the system, you know that nobody is making progress, right? So by monitoring CPU utilization, generally they do that at 40%. So if CPU utilization is below 40% and there are lots of processes, then there's an indication that nobody is making progress. So monitor CPU utilization, then you select a victim process. All right, this is a low priority process which is holding up this particular resource. Let us suspend it. Let us suspend it so that it releases, it is forced to release a particular resource, which is essentially what? Our third condition was no preemption. We are doing preemption, right? So we are sort of breaking that. We are preempting the process, selecting a victim process, snatching away its resource, giving it to some other processes that can use it and make progress. So that would be one way of dealing with allow the system to enter a deadlock and then recover from it. There are other ways of doing that. We'll talk about them. Next, ignore the problem altogether, which is done by Unix and Windows, because the disease is better than the cure. In order for having this complexity in the OS to prevent deadlocks or to recover from them, there's a lot of overhead that is involved. In fact, users get annoyed more about that rather than just maybe restarting their laptops or computers once in a while. Nowadays, deadlock conditions are occurring a lot more than they used to earlier. If you guys remember blue screens popping up indicating a deadlock situation, that used to happen a lot less earlier. It happens a lot more now because of how much we have started doing on the application layer. So, but that's still better. So it's interesting for a user psychology, right? It's better for me to just restart the computer once in a while rather than have it constantly being slow or constantly being dragged by this aspect of the operating system. So that's what they do, pretend that the deadlocks never occur, which is essentially used by most operating systems. The cure is worse than the disease here. Next, deadlock prevention. So how do you prevent it? We'll talk about how do you recover from it later. How do you prevent it? So we had 4 of those conditions. You guys remember, we had mutual exclusion, we had hold and wait, we had no preemption, we had circular wait. If we are able to prevent those 4 conditions from happening, then we are increasing the chances of not going into deadlock. So restrain the ways requests can be made. First way of preventing deadlocks is by breaking mutual exclusion. So instead of only one process can ask for one resource type, now we can say not required for shareable resources, must hold for non-shareable resources. So if you are having shareable resources, multiple processes should be able to use them, right? So read-only files, for example. Then you are breaking mutual exclusion. So mutual exclusion is only holding true for non-shareable resources, but for shareable resources, you are allowing multiple processes to use that read-only file, for example, as that resource. So what is going to happen? For all the shareable resources, you have broken mutual exclusion, moving you towards less chances of deadlock. Next, hold and wait. Must guarantee that whenever a process requests a resource, it does not hold any other resource. So if you are requesting for a resource, make sure that you are not holding a resource. So you cannot hold and then wait, ask for more. So go ahead. All of them at once, right? So, okay, whatever I have, do you have it available or not? The state of the system. If you don't have it available, don't give it to me. I will starve. Once you have things ready, I will take all the resources, use them, and I'll release them. Again, but you raise an important point. What if that resource never comes available, right? So suppose the process needs 4 resources, 3 of them are available all the time, 1 of them is not. It is going to have starvation. So process starvation is the consequence of not addressing deadlock properly. So if you don't do it, starvation can happen. Like I said, require processes to request and be allocated all its resources before it begins execution, or allow process to request resources only when the process has none allocated to it. So a process can only request resources when there is none allocated to it. So you're not holding and waiting. Or I'm going to assign you resources all at once or none at all. Right? So if I do all at once, then you will be able to use them and release them. The problem over here is poor resource utilization. What does that mean? So take an example of a process, like you said, four resources, right? So there is a process P1, it needs 4 resources. And one of the resources it needs is a slow hard disk, right? It has to write to a slow hard disk. Now, what is going to happen? It is, if we are doing this, right? We are saying that if I have the 4 resources that are available, I will take all of them, I will make progress, and I will release for all the 4, right? During this time, what is going to happen? I have taken 4 resources. Most of my time is being spent on that slow resource, the writing to the hard disk, while I'm still holding the 3 other resources, right? I'm not using the 3 resources during that time, but I'm still holding them during that time. You guys see that? So that's poor resource utilization. If I break, hold, and wait, then one problem is starvation. We talked about that. The other is poor resource utilization. You guys see how this is related? Starvation is very obvious, right? So if I have only 2 options, none at all or all of them at once, then all of them at once is my only option to make progress. And all of them at once may not happen because, say, there's only one resource, one instance of a resource, and it is always in demand, and higher priority processes are asking for it. I'm never going to get it, or I'm going to get it very late. So I'm going to be starving until that time. Process starvation is process waiting for a resource and unable to make progress. Next. So we try to break mutual exclusion. We try to break, what is that? No hold and wait. Now we are trying to break no preemption. So how can we break preemption? Well, let us do preemption. So if a process that is holding some resource requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. So if you request a resource that I'm not able to give you, then you're anyway not going to make progress. So you release all your, not voluntarily, but the OS is forcing you to, preempting you to release all the resources that you have assigned. So only use the resource if you are making progress. If you're not making progress, then you release all the resources. But because you have not made progress and you have released them, you will need to restart at a later point. So process will be restarted only when it regains its old resources, as well as the new ones that it is requesting. So no preemption, you break no preemption by allowing the OS to preempt a process. And you are preempting that process based on whether you are holding a resource or not. So if you are holding particular resources and you're waiting for others, you can preempt it, release all the resources that you were holding, and then we'll say, okay, we'll try later, right? So we'll try later is whenever I get my old resources back and there are new resources that are available for you to make progress, then I will try again and process make progress at that time. So that's deadlock prevention by allowing the OS to preempt processes. Circular wait. How can we break circular wait? Well, over here, circular wait was had to be in this particular order, right? P1 waits for P2, P2 waits for P3, P3 waits for P1, right? There was a sequence to this: 1 to 2, 2 to 3, 3 to 1. There was a cycle because of it. And in our general case, we said P0 to P1, P2, P3, Pn. Pn is waiting for P0. So that's a circular wait. What if we break that, right? What if we impose certain other order of process execution so that circular wait never happens? So that is how we break circular wait. Impose a total ordering of all the resource types and require that each process request resources in an increasing order of enumeration. So essentially, we are saying P0 is requesting for R0, P1 is requesting, we are forcing a certain sequence of requests and allocation such that circular wait doesn't happen. All right, let's move on to, can we detect deadlock? There is a algorithm called a safety algorithm. It's also called Banker's algorithm. that helps you to detect whether there is deadlock present in the system or not. So we are going to first allow the system to enter deadlock. And then we are going to see if we can use an algorithm to detect whether there is a deadlock or not. And then we'll talk about a recovery scheme from it. Next, recovery scheme is one of the simplest ways to do what? Select a victim process and kill it. So let's talk about the banker's algorithm or safety algorithm to detect deadlock. So before we actually get there, we'll talk about how do we sketch wait for graphs which do not involve resources, they only involve processes. So for example, if you only have single instance of each resource type, then why should I draw resource types in my graph? I will just draw processes in my graph. So suppose, if I go back here, maybe this is better. Yeah. So if suppose I have R1, one instance here, even if R2 had just one instance, instead of me saying P1 is waiting for R1 and R1 is assigned to P2, I could have said P1 waits for P2, right? I don't even need to talk about R1 in that case. So that's a wait for graph. P1 is waiting for P2. P2 is waiting for P3. P3 is waiting for P1. So not talking about resource, not drawing resources because we only have single instance per resource type. So if you have a single instance, we maintain a wait for graph instead of a RAG, resource allocation graph. Nodes are only processes. We are not including nodes that are resources. P sub I directed edge to P sub j indicates process I is waiting for process j. So we can periodically invoke this algorithm that searches for a cycle in that graph, and if there is a cycle, then there exists a deadlock. So from depending on the state of your system, you can invoke an algorithm that will detect for a cycle in wait for graphs. And if there is a cycle, then you know that deadlock will exist because two things are being satisfied: circular wait and mutual exclusion, right? Because of the single instance of each resource type. Now, such an algorithm, to detect a cycle, it is going to take you order of n squared operations, where n is your number of vertices in the graph. So it is going to have an overhead, which is what is the sort of a thing that the operating systems like Windows don't like to have, which is why such things are not implemented in real operating systems. So here we have an example where we are translating a resource allocation graph to a wait for graph. So let's see, P1 is requesting for R1. R1 has been assigned to P2. So that means P1 is waiting for P2 right there. And then P2 is waiting for R3. R3 has been assigned to P4. So P2 is waiting for P4. Similarly, P2 is waiting for P3 right there. Then P3 is waiting for P4 right there. P2 is also waiting for P4 right there. And then P4 is waiting for P1 right there. Is there a cycle? Well, yes and yes. So that you know that there is going to be a deadlock there. So invoke, translate. So for this applies for resources with single instances. Graph it out as a wait for graph, of course, using an algorithm, and then invoke that algorithm to detect the cycle after certain timed intervals. So again, it'll come down to how often should you do it? Performance versus your speed, right? So if you invoke such an algorithm too often, then you're slowing the system down because of that overhead. If you don't invoke such an algorithm too often, then you're risking the chance of deadlock being there and you not being able to detect it. Right? Now, if you have several instances of a resource type, then you cannot deal with that in a wait for graph situation. Then you would have to have some other algorithm that helps you detect deadlock, whether deadlock is present or not, which is a banker's algorithm, safety algorithm. It's a pretty straightforward and popular algorithm to detect. So banker's algorithm, why? Because bank tellers should be able to give money as much as they have, right? And they're giving it to multiple people. So they cannot give you more than what they already have. And they have to keep track of that. So that's sort of how it is related to our context here. The OS cannot assign certain resources if it doesn't have it available. So it's going to essentially monitor inventory of resources and instances of each resource, and then only be able, and with that, while monitoring how much each process needs, I will be able to know whether I have enough money in the bank to give to people or not, because I know how much I have and I know all the requests, how much money they're asking for. So that's essentially your safety algorithm in a nutshell. So in order to do this, we are going to need certain matrices with some numbers that will tell us instances per resource type that are existing and that are being requested. So what is available, right? So available is a vector that is of length m. This guy indicates, available vector indicates the number of available resources of each type. So suppose you have 3 resource types, say R0, R1, R2. Each resource has 2 instances, right? So 2 instances for R0, 2 instances for R1, 2 instances for R2. Then your available vector is going to be of length 3 with values 2, 2, and 2 in it. Right? So that's your available vector. That's how I understand how much is available in my bank that I can give. Now, this is going to be for all the resource types. Next, allocation. Allocation is going to be a matrix because this is going to be each resource type for each process. So n by m matrix, n is denoting number of processes, m is denoting number of resource types. So this is going to be a matrix that defines the number of resources of each type that are currently allocated to each process. Next, request. N by m matrix. Allocation is how much resources, instances of each resource type is allocated to a particular process. This is requests by that particular process, right? So n by m matrix indicates the current request of each process. I need 1 instance of R0, 1 instance of R2, and 0 instances of R3, right? So for that particular process, that nth entry, for nth process, my request is going to be 110. And then for next one, and then for next one. So we are going to have a matrix of requests. So how do we read this? Say, suppose you have that particular entry, a particular entry in that matrix, request, the row number is I, the column number is j, and that particular entry, if it is k, that means that process P sub I is requesting for k more instances of resource type Rj. Right now, it might be a little bit hand wavy, but we'll take a look at a detailed example with numbers. So hopefully, all of this will boil down to very, very, very simple things. Step 1, how do you, what are the steps that are involved in this algorithm? Step 1 is to initialize 2 vectors, work and finish. These are going to be of length m and n, where n and m are, this is number of resource types, and n is what? Number of processes. So first thing we do, we have those two vectors. We are going to initialize them. We are going to initialize work to whatever is available. So it's like the front end of your bank, right? They are going to need to know how much is available at the back. So work is available. That's what I can work with. Next, we are going to see whether certain processes are already finished or they need to finish. And we are going to monitor that by looking at their allocation. If the allocation to a particular process is non-zero, that means they still need to finish. So finish entry, right? The entry in finish is going to be false for those particular processes. So I have certain things allocated to me. Clearly, I have not finished yet, because if I did, it would have been 0. So then I initialize finish of I for that ith process to be false. However, if allocation is 0, that means that that particular process has already worked on things and made progress and finished and released all its allocated resources. That's why allocation went to 0. So then I can make that particular entry in the finish vector to be true. Now my goal is, the worst case scenario, what can happen? All of the processes initially are false. I'm going to need to figure out a way to make progress and get all the processes to the true, right? All of them to finish. Next, once you have initialized those vectors, work and finish, then we are going to find index I. Essentially, we are going to try to find a process I that can use whatever is available, work, and make progress, right? So we will try to finish, and we'll pick the one that has not finished already, right? So we'll pick the one that has not finished. The request for that particular process has to be less than or equal to work, right? It should be requesting for instances per resource type that are less than or equal to the amount you have available in work vector currently. Now, if that particular process exists, then you can assign it those resources. It will make progress and it will finish. Once it finishes, what is going to happen? Once it finishes, the allocation for that particular process is going to go to 0, and we are going to increase our work vector, because we are going to increment the work vector with the allocation of whatever just finished. Right. Resources of each type, work vector will include instances per resource type, but it is not for each process. It is for whatever is, yeah. So instances per resource type, yeah. Right. So once you finish, you are going to give it back, right? So when you give, what that giving back means is work will get incremented by the allocation for that ith process, because it got completed. Now, that's step 2. But what if you are not able to find anything that needs working on? What if there is no such I that exists? Meaning, everything has already completed, or I'm requesting for something that is more than my work, more than what is available. In that case, you go to step 4, which is essentially going to tell you that there is a deadlock that is present. So let's move, that's step 4, coming later. Next, step 3. Step 3 was, we figured out which process we need to work on. We made sure that our request was less than or equal to work. We made progress on it. We finished it. Once you finish it, we are going to increment work by allocation for that ith process, right? So whichever process we just completed, we are going to give back the resources to available, which is your work. And then we'll set that finish entry for that process to be true. It got done. Then we'll go back to step 2 and then do this for all the other processes that are there. Right? So step 2, again, we'll find that index which is false and work on it, work on it, work on it. Now, let's talk about step 4. Step 4 is, if you still need to work on certain process, finish I is equal to false, and there is an I between 1 and n, so process between number 1 and n, in which request is more than work, which essentially means there is no process that is requesting for something that I can give you. Right? Work is always falling short. If work is always falling short, then P sub I is deadlock. You guys see that? So this, we go to step 4 if step 2 doesn't find an I. Step 2 doesn't find an I means this guy is broken. It's not satisfied. You're requesting, the ith process is requesting for something that is greater than work. Well, if there is no such I that exists, then you are not going to be able to make progress on any processes. Only when finish is false. If finish is true, then you don't need to worry about deadlock. If for all the processes you have already finished, then there's no point in worrying about deadlock or not. Now, this particular algorithm requires a higher order of operations. So this is big O of m times n squared, m being what? No good. 0 to n minus 1 or what? There's no. I think I was consistent here, right? Like I said 1. Yeah. These guys are bankers. That's why. They would freak out if things started at 0. All right, so this is a higher overhead for this particular algorithm. The one that was for wait for graph was order n squared. This is big O of m times n squared, m being number of resource types, n being number of processes. So again, it again adds to that cure is worse, right? So disease is better almost. All right, let's walk through this example. So all of the things that we have discussed earlier with step 4, those 4 steps are going to be hopefully be crystal clear after this. So we have 5 processes. So our n is 5 here. N is 5. P0 through P4. All right, this was process. So we are back to computer architecture. So I can use P0. P0 through P4. 5 processes. There are 3 resource types, A, B, and C, or R1, R2, R3, whatever you want to call it. A has 7 instances, B has 2 instances, and C has 6 instances. This is in total. That is how much is there in the system. 7 for A, 2 for B, and 6 for C. And the snapshot of the system at some time T0, or T1 is this, right? The snapshot is this. So you are given the allocation matrix, right? 5 rows, 3 columns, n by m. And again, request is a matrix, 5 rows, 3 columns. Per process, how many instances per resource type are you requesting? So for example, so let's take a look at allocation, right? So 3 instances of resource type C are allocated to process 2, and so on. At that particular time snapshot, whenever that was taken, process 1 was requesting for 2 more instances of resource type C. Now, available is nothing at the beginning. Just so happens that at the beginning we don't have anything available. So that's a very bad start. Let us see if we have deadlock or not. So what do we do in step 1? We initialize work and finish, right? So initialize work and finish. Work should be initialized to available. And how should I take care of finish? Well, I can take care of finish by looking at the allocation matrix. Is any row zeros? No, 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 no. Which essentially means that all these processes will need to make progress still. Nobody has completed. So everybody is false. Oh boy, this is going to be tricky. All right. So F, I wish I had straight lines. All right, everybody is false. Go ahead. Oh, it does, it does. But that's sort of where I'll start things. But before I do that, I'm going to say, all right, are they already done yet? They are not, right? Yes, you're absolutely right. That's step one. So step one is done. I've initialized work and finish. Step two is I will try to figure out a process that can make progress. So I'm going to compare two things, work with request. So here I have 0, 0, 0. Here I have 0, 0, 0. All right, so that's good. P0 can make progress, but also P2 can make progress, right? So here is a choice for you. P1, P0 can make progress, P2 can make progress. Which one will you choose to make progress? P2. Okay, so I would have said the same. Why did you say P2? More resources are assigned to it. So once P2 gets done, it will release 3 instances of resource A, 3 instances of resource C that may be good for whatever comes next. So that would have been a better choice. But if I do that, then I'm almost guaranteeing here that my algorithm will flow very, very smoothly. But I want to make it a little bit tricky for myself. So what I'll do is I'll let P0 finish. That will be too simple then. All right, so if I let P0 finish, but with this discussion, you also know that there are multiple ways of making progress, right? So there's no one way. An operating system may choose one or the other, and a good choice is to choose the process which is holding a lot more resources than the one that is holding fewer resources, fewer instances of a particular resource. But also, okay, so here, there's a lot more to it. It also depends on what type of resource is being held, right? So if it is a very important resource which is being used by certain high priority processes, then you may want to work on that first so that it releases that resource. But if we don't have that information a priori, then we work on something that is holding more instances, right? So the numbers in the allocation matrix are more, work on that. All right, so let me make progress on P0 first. So if I make progress on P0, because request is less than or equal to work, P0 can finish. Once P0 finishes, I need to go back and update two things. One is the work vector, work equals work plus allocation. Allocation was 0, 1, 0, so that becomes 0, 1, 0. And I've already finished working on it, so this becomes true. Right? Next, I'm going to do this again, like repeat this same exercise. So 0, 1, 0. Now can I work on, so this is already done. I don't need to work on that anymore. Can't work on this, can't work on this, can't work on this. Oh, sorry, what am I looking at? I need to request. Can't work on this. Yes, I can work on it. No, no. So the only thing that I can do now is P2. No other choice. So if I work on P2, yes, request is less than or equal to work. I will be able to make progress. Then P2 will release 3 and 3 here, right? So this guy and this guy becomes 3 and 3 here. And this guy becomes, no, not that guy, P2. Yeah. So P0 finished, P2 finished. What next? I think I have all my options open. With 313, I think I can tackle anything. All right, so let's just do P1. Again, it's not unique sequence. Multiple sequences are there. So let's do P1. So if I do P1, two instances of resource type A will be released. So this guy will become 5, and this guy will become 2. True. Yeah. Next, with 513, I can do anything. Let's do P3. So if I do P3, it'll release 211. So they get added to this. So this becomes 7, 2, and 4. 7, 2, and 4, and this becomes true there. And then, of course, last one. So uses that, releases 2. So we go back to that, and this goes to true. 7 to 6, right? So there's a quick check whether we got back whatever we had in the system or not. Questions about this? So no deadlock present. All the 5 processes were able to finish. You guys see that? But the order in which they finished is not unique. Certainly, we talked about a couple of options already. Now, if you look harder, you may find a few more. Okay, next. What I want to do is give you guys another situation where deadlock could be present. This made progress, right? So what we'll do is, maybe in a different color, say blue. I will go back to step 1. Step 1 was all of these guys were 0 and everything was false, right? That was step 1. And I'm going to make an adjustment on something. I'm going to say P2, let us make this guy a 1. Right? So this is my problem now. Find whether the system is deadlocked or not. Right? So I've gone back to work, I've initialized, finish. I've kept everything the same except for this. I've changed one entry in this. So let's try to do this, the whole process again. The first step is you will compare work and request. You will be able to make progress on P0, only P0. When you make progress on P0, it will release one instance of B and it will be able to finish. So this guy will be 1 and this guy will be true. Yeah. How about now? 0, 1, 0. I cannot make progress on any process, right? P1 needs more, needs more, needs more, needs more. Don't have anything. Go ahead. Right. No, doesn't, because it is holding these many resources while it is saying I need one more of this. So yeah, so if I'm requesting for more, I've already held. So yeah, you can break that, right? So right. So in the detection, when we talked about detection prevention, deadlock prevention, we said if you're doing this, if you're holding certain things and waiting for some other things, don't do it. We'll preempt you so that you release whatever you are holding so that other people can make progress. So that's how we were doing the deadlock prevention. But here, you're not doing that. This guy is just holding on to this and then waiting for this one little piece here, which is not there. Right? So here there is a deadlock that is present. In the second scenario, P0 was able to finish, but nothing else. No other process will be able to make progress. So that's how you would detect deadlock. And the scenario is what? The scenario is multiple instances per resource type. So that's exactly what we have we have already done this. The example here is P2 is requesting for one additional resource type of instance, resource type C, one more instance. And what we found out is the system goes into a deadlock situation. Can reclaim? Yeah. So when we did this, we could have reclaimed the resources that were held by P0, but it was insufficient to fulfill other processes' requests. So P0 was able to finish, but nobody else was able to make progress. So deadlock consists of P1, P2, P3, P4. These are the 4 processes that are involved in the deadlock. All right. So we were able to detect it. Now, how will we be able to recover from it? Now, if suppose you are here, right, and you are given the choice of recovery, how would you recover it? Right. So here you have that. So P0 was done, and you entered the deadlock state. How would you recover it? Maybe you just suspend P2. Right. You just say, all right, P2, enough is enough. You are taking too much of my resources, and you're not making progress. Release all your resources. So suspend it, take the resources, use it for making progress in other processes, and then later on, when you have time and resources, you can come back to P2. So you could select. Now it's about selecting which process to suspend. A bad option is suspend all the processes and restart all of them. That's a bad option, but that's an option. A better option is choose one victim process, suspend it, but with that comes another difficulty. Because when you suspend a particular process, you are essentially going back. So you store the current state, you suspend it, so you'll have to restart it. When you restart it, it has to sort of be consistent with how much ever you have worked on it already. Right? So that's sort of the difficulty over there. Let's talk about the detection algorithm usage. So how often do you use this detection algorithm, whether it be for the single instance type with the wait for graphs, or whether it be the banker's algorithm? It will depend on answers to these 2 questions. How often does a deadlock likely to occur? So if it is regularly happening at certain time intervals, then you would want to invoke this detection algorithm a little bit earlier than those, in shorter intervals, depending on the frequency of the deadlocks. Next question that is related is, how many processes will be affected by this deadlock if it occurs? If it is only affecting 1 or 2 processes which are not critical to the system, then you may choose not to invoke the detection algorithm because the price you pay is not severe. However, if it is engulfing too many processes, then you would want to invoke the detection algorithm very often to make sure that you detect and then be able to prevent it from happening. Next, invoking the detection algorithm for every, so the answer is, you could do it at every resource request. Every time a particular process requests for a resource, you could invoke this detection algorithm, or you can do it, say, once per hour or at certain defined interval. Like we said, we can monitor the CPU utilization, and if the CPU utilization is below 40%, you can invoke this particular detection algorithm, because you know that if the CPU utilization is low, you're not making progress. You're not using the CPU to make progress on the processes, which gives you an idea that there is some deadlock happening or slowing of the progress. More processes are entering the waiting state. Now, in order to recover from a deadlock, we do process termination. We select a victim process and terminate it. So we have a few related questions to ask about, essentially regarding which one to pick as the victim process. So about all deadlock processes is one option, but it's not the best option. So in our example, we had four processes that were deadlocked, P1, P2, P3, P4. If we aborted all of them, it would have released a lot of resources which we could have made use of them, or by restarting those processes. But we could also get the same thing done by choosing one victim process. So the second option over here is abort one process at a time until the deadlock cycle gets eliminated. And in our example, if you had eliminated just one process, say P2, I think you would have got 3 resource types of A, 3 from C, and you would have made progress, and you would have been okay. Now, If you're choosing this one process, then the questions are, which one are you going to pick? Are you going to pick, in which order are you going to choose which one to abort? Are you going to base it on the priority of the process? Are you going to base it on the number of resources that are being used by that process? Are you going to base it on the number of resources that it is requesting? Are you going to base it on how many processes will need to be terminated? If I choose this particular sequence, then I need to terminate 3 processes, versus if I choose this particular sequence of aborting processes, then I only need to terminate 2 processes, right? So all of these are related questions to how you pick the victim page, not victim page, victim process to terminate. Next, selecting that victim, you're trying to minimize the cost, and cost could mean a response time, right? So it could mean if I only terminate one, then the price that I pay of terminating processes is just for that one process, as opposed to if I select some other process to terminate, I may end up terminating 2 or 3 more processes, right? So depending on cost, and we have provided some metrics of cost. Metrics of cost could be priority, it could be resources that are being used or that a process is requesting. So based on certain criteria, we could say we will select that particular victim process, or we roll back. So rollback is return to some safe state. So certain process is requesting for a resources. So there are requests for resources. Instead of them being active processes, what we can do is we can roll the process back to some safe state and then release the resources. The process releases the resources so that it can later start at that particular safe state. Now, like I said, the only trick about this is consistency between those states, right? If you roll back to a particular state, release the resources, those resources are being used by some other processes. At a later time, you want to restart that process from that safe state, it has to be consistent, right? So that's a little bit of a challenge there. Next, starvation. So starvation is the same process may always be picked as a victim. So include number of rollback in the cost factor. So if you have done this rollback for a particular process many times, then we are not going to penalize that same process even more, because that is leading to process starvation. And we can do that by including that rollback in the cost factor for that. So when we try to minimize cost, then we don't penalize the same process over and over again. All right, I think this is it for deadlock. I see that you guys are very bored, so I'm going to stop recording here.